Hello, and welcome to this film, which is all about gas laws. Now, these are laws in the sense that these are things which are often obeyed, but not always. And hopefully by the end of the film, you'll see what we mean by kind of normal conditions, where these laws are obeyed, and what they tell us about the behaviour of gases. And you'll also see some of the units that we often use when we're talking about gases in general and discussing these laws as well. Okay, so let's start off by looking at something called Charles's law. And as with all these laws, the name of the law isn't all that important. It's knowing what the law tells us. Okay, so this law tells us that if I double the temperature of a gas, its volume will double, as long as the pressure remains constant. Or if I halve the temperature, the volume will halve. And this diagram here shows us we've got a cold gas, relatively cold, and a relatively hot gas, and the hot gas is taking up more space. What you might notice here is that the temperature is given in two different units. There's actually a typo here. This should say 27 degrees centigrade. And that's because they're giving us the temperature in degrees centigrade, and they're also giving us the absolute temperature in Kelvin. And you might remember that absolute zero is minus 273 degrees centigrade. This is where the Kelvin scale starts. This is 0 Kelvin, or absolute zero. It's a theoretical temperature which we can't actually reach. But 1 on the Kelvin scale is exactly the same temperature change as 1 on the degrees centigrade scale. It's just that they start in different places. So if I add 273 to the degrees centigrade temperature, I get the absolute temperature in Kelvin. So 27 degrees centigrade is 300 Kelvin, 327 degrees centigrade is 600 Kelvin. And it's very important that we use the absolute temperature if this law is going to work for us. So if I double the degrees centigrade temperature, the volume won't necessarily double. But if I double the absolute temperature, it will. It's a little bit confusing because this graph shows the temperature in degrees centigrade. But really, the relationship here is between the absolute temperature and the volume. Notice that the volume here is given in milliliters. Okay? And this is quite unusual to see in the IB because 1 milliliter is equal to 1 centimeter cubed. Okay? So they're the same amount, they're just a different unit for that same amount. And it's very rare to see the milliliter in the IB. It's also worth knowing that there are 1,000 centimeters cubed in 1 decimeter cubed, or a dm cubed. Now most people in sort of everyday life call that 1 litre, but we don't use the litre in the IB, we use the dm cubed. And as you can see from this graph, right, we've got this straight line relationship showing that there's a directly proportional relationship between the absolute temperature and the volume. What you can also see is that there's a dotted line here showing that this line's been extrapolated. Okay, and this is happening at about minus 200 degrees centigrade, where this law stops working particularly well because the particles are now so close together that the assumptions that we make about the particles having no volume and not attracting each other at all, they're not valid assumptions anymore because the particles are so close together. So this law stops working. And if you think about it, when the particles have stopped and they're as close together as they can be, the volume is never going to reach zero. The law says that if I get down to minus 273 degrees centigrade, or 0 Kelvin, and the particles have stopped, we're assuming that the particles take up no space, so the volume is zero, but obviously that makes no sense. But the assumption works quite well if we're in the kind of normal temperature range, or at temperatures higher than about minus 200 degrees centigrade. What does this law mean for us in practice? In other words, can we put it into some calculations? Well, if V is proportional to temperature, that is to say V is proportional to T, then V is equal to a constant times the temperature. Those two things are saying the same thing. If this is true, then V over T is equal to a constant, which means that V over T will be a constant value. V over the number that I get if I divide the volume by the temperature for a certain amount of gas will never change. Okay, so this is like saying that V1 over T1, my original conditions, are always going to be equal to the new volume and the new temperature if those conditions change. Okay, so V2 over T2 equals V1 over T1. Let's put this into practice here. So a balloon containing 2.0 decimeters cubed of air is heated from 20 degrees centigrade to 40 degrees centigrade. What volume will the air occupy at the new temperature? Well, first of all, as we've seen, it's very important to turn these temperatures into absolute temperatures. So we're going from 293 Kelvin to 313 Kelvin. Okay? And so the temperature has changed by a factor of 313 over 293, and that equals 1.07. So in other words, the temperature is increased by that factor. The volume will also increase by that factor. So it will go to 2.14, but I can only give it to two significant figures because that's my least precise bit of data. So it will increase in volume to 2.1 dm cubed. That's kind of thinking about what will happen in kind of common sense terms. If you prefer the formula, then V1 over T1 equals V2 over T2. We're being asked what the new volume is, which is V2. So V1 over T1 times T2 is equal to V2, the new volume. But notice that if I plug some numbers in here, I'll be plugging in T2, that's my new temperature, 313, T1, that's my old temperature, 293, and I'm multiplying it by the volume, 2. So I'm doing exactly the same calculation, I should get exactly the same answer. But some people prefer the formula rather than figuring out each time what's going to go on. Okay, let's move on to the next law. This is called Avogadro's law. Here's a picture of Avogadro, one of a number of scientists who were working at gases around the same time as Charles and Dalton and Boyle and people like this. But anyway, he said that the volume of a gas is directly proportional to the number of moles of that gas. So the more particles you have in a container, the larger its volume will be. And not only that, if I double the number of particles, then the volume will double. Now he's saying that this works for all gases. If this is going to be true, then we have to assume that all gas particles are infinitely small, so that the size of the gas particles doesn't actually affect how much space they take up. Okay, and again, this assumption works pretty well, but it makes no sense really to say that all gas particles will be the same size because they're all different sizes. But it works quite well for us. What does this mean in practice? Well, once again, if we say that V is proportional to the number of moles, then this is the same as saying that V is equal to a constant multiplied by the number of moles, in which case the volume over the number of moles is a constant, and so the value of V over N does not change for a particular gas. Okay, so in other words, if my original volume and my original number of moles changes to some new volume and some new number of moles, then those two values have to be equal. Okay, so an elastic container containing 0.25 moles of methane has a volume of 2 decimeters cubed. Another 0.1 of a mole of methane is injected into it. So we're going from 0.25 moles to 0.35 moles. So the number of moles has changed by a factor of 0.35 over 0.25. And what does that equal? Well, that equals 1.4. So my volume is going to increase by a factor of 1.4, and 2 times 1.4 is 2.8, but I've only got one significant figure, so it's going to take up 3 dm cubed. Okay, so the volume increases if I increase the number of moles. That makes sense, right? Assuming the temperature doesn't change, of course, because temperature might have as an effect on this. As we've seen before, the volume is proportional to the temperature. Now, if I just wanted to use the formula again, then my original volume is V1, that's 2 dm cubed. I'm trying to find the new volume, that's V2. So V2 equals V1 multiplied by N2 divided by N1. Okay, so in other words, I'm multiplying my original volume, which is 2, by the ratio of the number of moles, so 0.35 over 0.25, and once again you can see I'm doing exactly the same maths here, and to one significant figure, because that's all I've got here, that'll be 3 dm cubed. Okay, let's move on to the last of the 3 laws that we're going to look at, and that is Boyle's law. Now, Boyle's law says that the volume of a gas is inversely proportional to its pressure. Okay, so in other words, if I plot the pressure of a gas, and notice here that the units of pressure we're being given are millimeters of mercury. It's worth noting that there are 760 millimeters of mercury in 1 atmosphere, So the pressure at sea level is 1 atmosphere, which is about equal to 101 kilopascals, which is 101,000 pascals, or 1.01 times 10 to the 5 pascals. Okay, so a few different pressure units there. Okay, and it's important that we know how to convert between them. There's 760 millimeters of mercury to every atmosphere. 1 atmosphere is equal to 101 kilopascals. Anyway, as the volume is increasing, you can see here, the pressure is falling. And this kind of makes sense, I suppose, intuitively, that if I expand the size of a container that's got some gas in it, the pressure inside that container will fall, because the particles will be hitting the walls of the container less often and so on. Okay? What this graph shows here is that if I plot the pressure against 1 over volume, I get a straight line. That is to say that pressure is directly proportional to 1 over volume. Okay, so that's Boyle's law. That's what it tells us about gases. Now, if we just put it into practice, say we have a look at a few problems, and like before, we'll put V is proportional to 1 over P. This is the same as saying that the volume is equal to a constant times 1 over P, or in other words, K over P, in which case the volume times the pressure is a constant, so long as the temperature and the number of moles doesn't change. Okay, in other words, P1 V1, as it's often written, is equal to P2 V2. Let's have a look at a calculation here. A syringe containing 50 centimeters cubed of oxygen at atmospheric pressure, remember this is 101 kilopascals, or 1.01 times 10 to the 5 pascals, is compressed at constant temperature until the volume is 10 centimeters cubed. What will be the pressure inside the syringe? We're trying to find the new pressure, that's P2. Let's just have a think about it though. Okay, we've got a container that's 50 centimeters cubed in size. We've reduced it to 1/5 of its size. So the new volume is 1/5 of the original volume. So if the volume is proportional to 1 over P, then the pressure should increase by a factor of 5 over 1. If you don't like doing those things in your head, then let's put it into the formula. Our original pressure is 101 kilopascals. Okay, we're multiplying that by the original volume, which is 50 centimeters cubed, but we don't want, we want the new pressure, so multiplied by 50 centimeters cubed, okay, equals P2 times V2, but we don't want the V2 over here, so let's bring it over here, and that's going to divide that, so 10 centimeters cubed, and you can see once again it's the pressure multiplied by 5 over 1. So the new pressure is going to be 505 kilopascals, or 5 atmospheres, or 5 times 760 millimeters of mercury, if you prefer. Okay, so that was a look at the 3 important gas laws that we need to know about. In the next film, we're going to try and combine them into an ideal gas law. But for now, hopefully you understand what we mean by normal conditions. That is to say, not extremely high pressures and not extremely low temperatures when the particles start to interact quite significantly. And you'll be aware of the units like millimeters of mercury, dm cubed, cm cubed, degrees centigrade compared to Kelvin, and so on and so forth. Okay, if you've got any questions, as usual, come and get some help with them as soon as you can, or post a comment on YouTube.